Okay. Let's see. Oh, are there any questions about material or procedural things? So we have, and let me just check that my actual headphones are connected. They are connected, in fact. Homework 1 is due at midnight. That's today. And submit via Blackboard. Okay, now, so continuing from last time, there was one thing that we left, and that was the case of complex roots. Well, we're also going to talk about double roots, but I didn't give you a complete account of complex roots. And so I'll show you an example. Let's consider A to be the matrix 4, -3, 3, 4. So the determinants of A minus lambda I is equal to what?
Four minus lambda squared plus 9.
Yeah. And that's lambda squared minus 8 lambda plus 16 plus 9, and that gives me 25. So lambda squared minus 8 lambda plus 25. And if we look at this, well, let's just do it. So negative lambda is, by the quadratic equation, 8 plus or minus 64. And then 4 times 25, that's minus 100. Divided by 2. And cool fact, so 6, 8, 10 is a Pythagorean triplets, because 64 minus 100 is minus 36, which is the square of minus the square of 6. So we get 4 plus or minus 3i. Now, so for lambda equals 4 plus 3i, let's find a eigenvector for this eigenvalue. And what we're going to do is we're going to consider the kernel of, it would be minus 3i minus 3, 3 minus 3i. And I'm going to write it in this row reduction procedure. Of course, what happens is that both of these rows are multiples of one another. So there's really only one equation. And that equation is that if we're solving for an eigenvector AB, then minus 3i times A minus 3 times B is equal to 0. So when we have something like this, it's under constrained and we can set A to whatever we want. Well, if we set it to 0, then B is 0, and then it's a 0 eigenvector, and that doesn't give us any information. We want a non-zero eigenvector. So let's A equal 1. And then what we get is, well, the 3's cancel out. And so B is equal to negative A IA, so negative I. So 1 negative I is an eigenvector. And what this tells us is that we have a solution, and the solution is 1 minus I times e to the 3 plus 4 plus 3i. T. And that can also be written as 1 negative I 4 e to the 4t by cosine of 3t plus I sine 3t. Now, what we're going to notice is the following. So the original equation is a x equals x prime, and a is real. So if this equation is satisfied, that if we take the real and the imaginary part of the equation, well, then a is entirely linear. So, and it's real. So it just commutes with the real part operator. And it implies that a of real x is equal to real x prime. And this is basically happens because a is real. And because something like differentiation is just differentiation of both the real and the imaginary part. So we can get real solutions from it just by taking the real and imaginary parts, right? That's pretty cool. And so what happens then is that if we have our original solution, let's call this star. Well, then star is equals to, and now we can split it up as, well, let's see what it would mean to get sort of a real part. So we have this times 1, and then we have I times this. So we get, well, I can keep the e to the 4t out front. And then we get cosine 3t. Then we get so in this component, we'd get I times I is -1 and then minus sine of 3t plus I e to the 4t. Then this term with this part, sine 3t. And this with this minus cosine of 3t. Thus, e to the 4t, the real and imaginary parts individually are solutions. Now, how does that square with the fact that we have another eigenvector, right? Because we found two solutions, and these two solutions are linearly independent. And so that should be all of the solutions. But we have another eigenvector unaccounted for. Will that give us different solutions? So with the other eigenvector, suppose lambda 1 is our first eigenvalue and its conjugate is equal to lambda 2. Because roots of real polynomials come in complex conjugate pairs if they're complex. And then what's going to happen is we're going to try and take the kernel of a minus lambda I. And if we have a vector in the kernel v that's equal to 0, then what that implies, let's say lambda 1, is that if we take the complex conjugate of both sides, I'll write lambda 1 bar. Now, A is entirely real, and complex conjugates distribute over multiplication, or of matrices in general. So we'll get V conjugates is equal to 0. Let's make this a vector. Thus, V conjugates is an eigenvector for V, for lambda 2. Now, let's think about what the general approach of the solution that we had was. We said, let's V equal, let's call it V1 plus I V2. So let's split it into its real and imaginary parts. Then what we claimed is that what we saw is that for the conjugates roots, the eigenvector would be V1 minus I V2, right? And what are the solutions going to be now? Well, the solutions, we have a solution and that solution is going to be V1 plus I V2 times, let's say lambda 1 is, how do I want to write this? For, let's say lambda 1 is equal to alpha plus I beta. Then it would be e to the alpha t times cosine of beta t plus I sine of beta t. And then if we rearrange that into its real and imaginary parts, what we'd get is V1, well, rather, let's keep the e to the alpha t out front. V1 cosine beta t minus V2 sine beta t and then I'll put blue parentheses around this. And then I'll write plus I. And then we have V1 I sine beta, so V1 sine beta t plus V2 cosine beta t. And had we used the complex conjugate roots, then what would have happened is that this I would have changed by a sign, but so would this. So for V1 plus I V2, sorry, minus I V2 times e to the alpha t cosine beta t minus, because it's now the complex conjugate roots, sine of beta t. What we get is that what happens is only the cross terms change sign. So we are going to get basically the same expression as here. Except for the fact that the cross terms are going to change. So this is going to become minus I, right? Because this term with the two minuses cancel out, it's only for the cross terms that the minuses don't cancel out. And so what happens? Well, then the real parts are the same and the imaginary parts are -1 of each other, but that gives us two linearly dependent things that are just related by a constant. So the real and imaginary parts that you get from either of the eigenvectors, they give the same basis of functions up to a sign. So you don't even have to solve for the other roots. Just taking the real and imaginary parts of the functions that you get in the first one let you solve the problem. So going back to this problem, that implies that the solutions are x is equal to c e to the 4t cos 3t plus d e to the 4t sine 3t, and y is c e to the 4t sine 3t, and I guess minus d e to the 4t cosine 3t. And that would be your set of solutions for this equation. So complex roots are actually not that bad. Last time it was a bit of a messier calculation, but this time it's pretty direct, right?
Could C and D the real numbers?
We want real solutions, and we got real basis things, so then we take real multiples of them. If we started off with this solution right here, so I can sort of show you what we did last time. So this is last lecture. At the end of the lecture, we got these functions, and instead of taking the, wait, is my, okay, something is wrong with my computer, and apparently my mouse is not working on, okay, well, it is now. So we took, in general, complex multiples, and then we chose these values very carefully so that we get real expressions. And this method works in this case, but it is sort of a more robust and general method of doing that solution is the one that I described right here, where you just find a single eigenvector and then you take the real and complex parts of that, well, real and imaginary parts. So that covers the case of complex roots, and that's pretty much all there is to say about them. Now let's get on to the much more interesting case. Well, I guess before we do, let's just take a look at the example that we just did. So the example that we just did was 4 minus 3, 3, 4. So let's plot the distribution for example 9. And you can see in this example, since sort of the exponential factor is pretty big, that it's very clearly spiraling outwards, right? If you follow this path along, it's clearly spiraling out. And pretty quickly at that. It would sort of look like this if I were tracing it back and forwards. So there's no like line or two lines as we saw in the previous examples. So to give you an example, like from before of what our distribution looked like when there were two real eigenvectors, it would look like something like this. In this case, we have sort of the 45 and the negative 45 degree lines. They're real eigenvectors. So along those lines, it just acts by scaling the vector by a certain number. And then at other points, you get curvy, interesting behavior. And this is if they're both pointing outwards. And if they were pointing one outwards and one inwards, then that was like a bit more interesting. I'm not sure which one of these looks better, EG4 or EG5. One of them looks better than the other. Yeah, this one's pretty clear. They're also the 45 degree lines as the eigenvectors. And then you get this. But if you have no real eigen values, then it looks like a spiraling thing in general, or inwards or outwards. Or if it's a purely complex root, then it's just perfect circles. And I think that was example 6. In this example, they're purely imaginary, and then you just get perfect spirals. Okay, so now let's do the far more interesting case of multiple roots. Okay, I'm going to stop sharing, and then I'm going to start sharing again under the hopes that this is actually going to cooperate for some reason. What's going on? That looks a bit better. Okay, multiple roots. So this situation is much less trivial than you'd actually think at first glance. And that's because you can actually get two different kinds of behavior with multiple roots. I'll show you the really simple case, case 1. And so case 1 happens when you have something like, let's say, A is equal to 2, 0, 0, 2. So this is just a multiple of the identity matrix, right? Cool. So, well, what's determinants? It's almost too easy to write out. It's factored already. So lambda is equal to 2 is an eigen value of multiplicity 2. Now, I mean, is there a preferred basis for this space? What do you think that if we plot this, the solutions are going to look like? So, okay, let's put this differently. If we look at A minus 2i, what matrix is that equal to?
Oh, nothing.
And so what are the eigenvectors?
Anything.
Yeah, so anything, it is an eigenvector. So no matter what vector you take, this is going to act by scaling on 2, right? And so we knew what the picture would look like if you were on a line, that it was an eigenvector, right? So if it's a positive eigenvector, where would it point? What would the arrow be at any point?
Out.
Yeah, outwards along the direction in which you're located, right? And so we can just confirm that. So if I do a repeated route along the lines of, let's do example 12. And let's make this 2002. And yeah, so it's just pointing out along every single line, except for the fact that these things like aren't drawn at the perfect places. So it might look like there's a bit of curving, but there really isn't. It really is just pointing outwards along every single line. If the sampling points were better chosen, it would look more like the case, but that's what the case is. So basically what happens then is that we have a kernel that's two-dimensional. So in this case, the kernel is two-dimensional. And so every single point in this two-dimensional space is an eigenvector. And then we can take any two linearly independent non-zero eigenvectors. Well, that's redundant. If they're linearly independent, then they're non-zero. So we take any two linearly independent eigenvectors. And since anything is an eigenvector, there are some sort of very obvious choices to make. Let's make them be 1, 0, and 0, 1. And so remember that the result that we saw last time was that if we had an eigenvector associated with a certain eigenvalue, then we'd get a solution to the original differential equation. And so this implies that v1 e to the 2t and v2 e to the 2t are solutions. Because that's how our onsets work out. We made the onsets that we have a vector times e to the 2t, and we saw that that would be a solution so long as the vector was an eigenvector. Well, here we have two linearly independent eigenvectors, and so we get two linearly independent solutions. So that's good. So writing this out, this says that x is equal to c e to the 2t, y is equal to d e to the 2t, is the general solution. And if you think about it, x and y sort of aren't interacting, because if you think about what the equations are, it's that x prime is equal to 2x and y prime is equal to 2y. So it's good that we found solutions in which x and y don't interact, right? Well, so you may think, okay, well, that's simple. So multiple roots aren't a problem. Well, then unfortunately, we get to case 2. And case 2 is, let's consider the example of a is equal to 2, 0, 2, except there isn't a 0 here. There's now a 1 here. So let's take the determinants of a minus lambda I. Well, the thing is that we get this term as before, and then this term contributes nothing. So it's still 2 minus lambda squared. So lambda equals 2 is still an eigenvalue of mults 2. But now, if we try and solve for the kernel of a minus lambda I, then we get 0, 1, 0, 0. And we're trying to solve for something in the kernel, so we put 0, 0 here. And so what that tells us is that if the eigenvectors of the form AB, then B equals 0, right? And then 0 equals 0, which is fine. That tells us that we can let A be anything we want, and it would still satisfy these two equations. So 1, 0 is an eigenvector. But we do not get a second linearly independent eigenvector. And so that's a problem. How are we going to find a solution? Because in general, the theorem should be that it's a linear, essentially second order system. It's a first order system, but it amounts to something that's morally like a second order equation. And so there should be two solutions that span the space. And so what do we do? Well, actually, we can solve this problem without using matrices. Let's think about the equation. The original system was, and so x prime is 2x plus y. And y prime is equal to 2y, right? So we're able to solve for y. What does y equal?
Oh, like, how do you want us?
So just looking at the second equation, this is a separable equation, right? And sort of you've seen this example enough times that maybe you can see what the solution is going to be right away with a constant.
I mean, e to the x. So e to the 2x? Oh, wait, no. Oh, yeah, e to the 2x.
E to the 2t. Let's use t as our variable. So c e to the 2t. Yeah. So perfectly formally, if you want to do it formally, you get dy over y is equal to 2 dx, right? So log y is equal to 2x plus log c. So y is equal to c, sorry, not x, we're doing it in terms of t. C e to the 2t, right? Good. Okay, so what happens then is that this reduces to x prime is equal to 2x plus c e to the 2t. And remember that x is a function of t. So it's a bit confusing with our previous things, but when the systems chapter, everything's a function of t, right? So it's fine. Well, what kind of equation is this? So I'll give you a hint. I could write it as, go ahead.
Oh, it's just like linear non-homogeneous.
Yeah. So first order linear. This is a first order linear equation. And we know how to solve these, right? So first we solve the homogeneous problem. And the homogeneous problem can be written as x prime is equal to 2x, right? And we know what the solutions to this are because we just literally solved this equation with x instead of y. So x is equal to, and this is sort of misleading because this isn't the same x as in the non-inhomogeneous thing. So we're solving the homogeneous problem. The solution to the homogeneous problem is x is equal to c e to the 2t. And now we're going to use what's the good technique for solving things that we use even for higher order linear equations?
Integrating variation parameters.
Variation of parameters. And so for variation of parameters, we use the ansatz that x is equal to what? By the way, I erased C because we only care about a particular solution at the moment. So we multiply this by what?
Oh, a general thing? Like,
yeah,
say,
an unknown function, u. And so what we get then is that x prime minus 2x equals c e to the 2t becomes, so u prime e to the 2t plus 2u e to the 2t minus 2u e to the 2t equals c e to the 2t. And so as a consequence, u prime, well, then we divide by e to the 2t on both sides is equal to c, right? So that tells us that u is equal to cx plus d. So that tells us that x is equal to c e to the 2t. C, sorry, it's not x. I keep making this mistake. We're using t as our variable. Ct e to the 2t plus d e to the 2t is a solution. Is the general solution. And now I wrote x here, but we solved for y before. Y was c e to the 2t with the same c. So I'm going to write y is equal to c e to the 2t. And then these two equations together give the general solution. So look, this problem has two solutions, right? But we only had one eigenvector. So that's a problem. We know what the general solution should be, but how do we do it using this eigenvector approach? And so back to the eigenspace approach. And so with the eigenspace approach, basically what happens is this. Here's the deal, the crux of the issue. If sort of lambda minus a to the power of, let's say, m is a root of the characteristic polynomial, well, it's the root, let's say it's a factor, because I didn't write a. Then we consider the kernel of a minus lambda I. And let's consider the dimension of the kernel. So first off, if you have something in the kernel of a minus lambda I, then that thing is what? I didn't hear that, but I think you probably meant to say eigenvector, right? So the crux of the issue is that we'd hope that this is equal to m, such that there are m eigenvectors, linearly independent eigenvectors. But the problem is that doesn't happen. There aren't necessarily m linearly independent eigenvectors. So what actually happens is that it's not the dimension of the kernel of this thing that's equal to m, but this thing to the power of m that's equal to m. So in general, if you sort of think about it, in the example 2102, if we considered a minus 2i, that equals 0, 0, 0, 1. And if we take a minus 2i and we square it, then we get a matrix multiplication. And then let's see what it looks like. Well, you do this by this and you get 0. Then you do this by this and you get 0 here. Then you do this by this and you get 0 here. And then you do this by this and you get 0. And then you do this by this and you still get 0. So that's equal to the 0 matrix. And so you can see that that has a two-dimensional kernel, right? But it's not the case that a minus 2i has a two-dimensional kernel. It's only the case when we square it that we have a two-dimensional kernel. And in general, this can happen in arbitrary dimensions. Because let's say you consider something like 2, 2, 2, 1, 1, 0. Then you can sort of believe me that the eigen value, this has an eigenvalue of 2 with multiplicity 3. And when we consider a minus 2i, then we get the matrix 0, 1, 0, 1, 0, like that. Then what happens if we square this? Well, what's going to happen is, I guess, just as a visual aid, I can put the matrix twice.
It's going to be zeros everywhere beside for like the last column in the middle.
So if we take this by this, right? Notice that we get 1 here and 1 here. So we get a 1, right? And that's in this entry. In the middle, if you're talking about the middle, then you'd get 0, right? Because it's 0 times 1, 0 times 0, 1 times 1. So the only non-zero entry would be where?
The corner.
Yeah, the top right corner. And now if you take the cube of this and you multiply it with itself, then you can check that a minus 2i cubed, well, that's equal to the 0 matrix. In general, you actually get a really cool pattern. If you take the matrix that has 1s on the super diagonal, so just above the diagonal and 0s everywhere else, and you raise it to higher powers, then the 1s move up until they disappear. That's what it's going to look like. So you can see that if you have like a 3-dimensional eigenspace, in general, you might have to consider the kernel all the way up to the 3rd power in order to get a 3-dimensional generalized eigenspace. So this kernel this is known as the generalized eigenspace. Now, okay, do you just take linearly independent vectors for the generalized eigenspace and then use those? Well, no, it doesn't work like that, because the ansatz that we got was that it has to be an eigenvector for the original thing to work, right? So you can't just take something in the generalized eigenspace and hope that it's going to work. So we need to do something more clever. So we're going to consider the ansatz. And this is sort of what we had when we had before. When we had something and it had higher multiplicity, we sort of multiplied it by t, right? So we're going to use the ansatz. And there are several iterations of the ansatz that you could use, but I'm going to tell you the correct one. It's x is equal to v1. Let's put a t on v1, I think. Yeah, let's put a t on v1. And plus v2 times e to the, let's say our eigenvalue is lambda. So if lambda, so this is going to be an ansatz for sort of a general case where you have a multiplicity 2 eigenvalue. So what would happen then? When would this be a solution to, so we have the equation a x is equal to x prime. And the question is, just using this ansatz in this system, what do we get? So for example, if v1 is equal to 0, then we just get our original ansatz. And the answer is, well, v2 has to be an eigenvector for that to work. So we generalize the ansatz to be of this form. And then let's see what happens. Well, x prime is equal to, well, so we can differentiate this or we can differentiate this. So if we differentiate this, then we get v1 t e to the lambda t. Let's keep lambda t out front. Then, or we could differentiate t to get v1. Or we could differentiate, when we do this, we get a lambda. We're differentiating e to the lambda t, so we get a lambda. I'll write it as lambda t. Or we could be differentiating t, so we get v1, or we could be differentiating this, in which case we'd get v2 lambda e to the lambda t. And a of x is equal to, well, t is just a constant. It's a function of t, but as far as the matrix is concerned, it's a scalar. So what we're going to get is, and so is e to the lambda t. So e to the lambda t is going to be a scalar outside of everything again. Then we're going to get t a v1. And here we're going to get a v2. And then multiplied by e to the lambda t everywhere. So if these two things are equal as functions of t, then the part that has t dependence has to equal the part that has t dependence, and the part that has no t dependence has to equal the part with no t dependence. Is that 100% true? Yes, it is. Because setting t equals to 0, we have that these parts are equal, and therefore these parts are equal, right? That implies that we have that, well, looking at the part with t, that says that a v1 is equal to lambda v1, right? So this 100% makes sense, because if we sort of okay, right. So if t were 0, then v2 would have to be an eigenvector, right? But if if v1 were 0, then v2 would have to be an eigenvector. But if v1 is not 0, then we get a more general condition. So v1 for this, it has to be an eigenvector, which is surprising, because usually you'd think that v2 has to be the eigenvector, but no, it's actually v1, and that's correct. And the second condition that we get is that a of v2 is equal to v1 plus lambda v2. And these equations can actually be rearranged into a minus lambda I v1 is equal to 0. And this equation can be rearranged into a minus lambda I v2 is equal to v1. So what does this mean? What this means is that we have a vector. This means that v1 is an actual eigenvector. So it gets sent by a minus lambda I. Let's write that in blue. What does a minus lambda I send v1 to?
Zero.
Yeah. Okay, break soon. And then what happens is that, look at this, a minus lambda I sends v2 to what?
V1.
Yes, so we get this interesting shape. So what happens is we don't get something, two linearly independent things in the kernel. We get one linearly independent thing in the kernel, and then one thing that gets sent to the previous thing, which then gets sent to 0. So this is clearly in the generalized eigenspace, because applying a lambda I to it twice sends it to 0, right? But it's not in the first eigenspace, because applying a lambda I to it sends it not to 0. By the way, notice that v2, you can add any multiple of v1 to it, right? Because that multiple gets sent to 0, so it doesn't affect where that v2 gets sent, right? So this is defined up to an additive factor of v1. So what's the summary then? Well, so we found that if we have something of this form, then we get a solution of this form, right? So then x is equal to, what was our ansatz? v1t plus v2. Well, let's write it like this. T e to the lambda t v1 plus e to the lambda t v2 is a solution. And the actual example that we were doing with 2102, we will do after the break. And so for some reason, there's a weird thing going on. Actually, wait, yeah, I think I might know how to fix that weird thing. No, that does not fix the weird thing. It is currently 6:57. So I can either do a 12 or a 17-minute break. Let's take a longer break the second time around. So let's resume at 7:10. Also, yes, this is a blowpie. Okay. So, right. So we had an ansatz, and this ansatz was completely independent from the first ansatz that we took. Well, let's see what happens in the system where we have, so for A is equal to 2, 1, 0, 2. We had sort of A minus lambda I 0, 1, 0, 0. And then we were trying to find an element in the kernel. And what we got as a result was B equals 0. So let's A equals 1 and 1, 0 is an eigenvector. But now we want to find something that gets sent by A minus lambda I to 1, 0. So now consider zero, 1, 0, 0, and the vector 1, 0. And so what this tells us in equation-wise, we also had the equation 0 equals 0, but that doesn't matter, is that B is equal to 1 and 0 equals 0. And we can set A to be whatever we want. So let's actually make it simple. We want a non-zero eigenvector. Here we had to choose A does not equal to 0, or we would have had 0. But here B is 1. So what should we let A be?
Zero.
Yeah, 0 is the best choice because it just leads to fewer terms. So let A equals 0 gets 0, 1, and we can't call this an eigenvector. This is not an eigenvector. However, this is V1, and this is V2. And what our ansatz said is that if V1 was the eigenvector and V2 was something that got sent by A minus lambda I to the eigenvector, then X is equal to, so T times the eigenvector, so T e to the 2T times the eigenvector, 1, 0, and then plus e to the 2T 0, 1 is a solution. Let's call this X1. What was the other solution from before? So just using the eigenvector ansatz, we have an eigenvector, right? So what's the associated solution?
Oh, just e to the 2t 0, 1.
0, 1. No, 1, 0. 1, 0 is the eigenvector.
Okay.
Right? Because that's the eigenvector. So that's the eigenvector. And so the eigenvector always gives us the solution from our original ansatz. And that our more sophisticated ansatz for the second order thing tells us that this is a solution. Thus, what's the general solution? The general solution is, and then we look at what's we get in the first component. So let's say we multiply, let's say this is sort of the first one we got. So despite the fact that I wrote a 2 here, let's put C here and let's put D here as their constants. And I'm not writing multiplied by D, I'm just saying that this is affiliated with C and this is affiliated with D. So then we get C in the first component and D in the first component here. So it's going to be X is equal to e to the 2, well, let's put the constants first. C e to the 2t plus d, so here t e to the 2t and y is equal to, well, it's just d to the 2t. And remember, what we did was we solved this system as a linear first order system after solving for y. And if we compare to our solution from above, what we had was, well, so there's t and not t, so we just switched the meaning of c and d. In there, we had c here and d here. So flipping c and d, just giving constants different names, we see that we have the same solution. So we are able to recover it. Yeah, so this matches with our previous solution. Now, what happens if I have a three-dimensional eigenspace and I have the bad case? So what if I have 2, 1, 2, 1, 2? Right? So we saw that in this case, if we look at a minus 2i, then that has a one-dimensional kernel. If we square it, that has a two-dimensional kernel. But if we cube it, then it has a three-dimensional kernel. So in general, we have to go all the way to the third power to get the kernel. So what would happen? Well, so the thing is that the dimension increases each time, right? And so the dimension increases each time means we can find something that's not in the span of the two previous items that gets sent to the previous item. So in this case, what we would hope for is to have v1, and that gets sent to 0. And then there's some v2 that gets sent to v1, and then there's a v3 that gets sent to v2. So because the kernel increases in dimension with everything, and we did this calculation before, we considered this example, and we saw that it's not 0, it's not the 0 matrix, so this is a two-dimensional kernel. This says that c is equal to 0, right? If it's in the kernel, so that's a constraint. So a and b can be whatever we want, but c has to be 0. So that gives us a two-dimensional kernel here. But then there's eventually something that's linearly independent from the things in the kernel of a minus lambda I squared that gets sent to inside that space after we apply it. So we're going to be able to find a sequence like this. Well, what's the ansatz going to be? So the ansatz is actually going to be slightly more clever. And I actually don't have this in my notes, so this might not be perfect. But the ansatz is going to be x is equal to, so we have v1, and we have t squared. Right? Last time we had t, now we're going to have t squared, but here's the catch. If we want this pattern to happen, we're actually going to have to divide by 2. Now, I'm going to tell you why the 2 is there when we do the calculation and see what this ansatz means. So the 2 should be there such that the meaning is this, because otherwise the meaning is going to be that this is multiplied by 2 somewhere. Okay, then t v2, and then v3. So with this ansatz, the equation ax prime equals x, ax, becomes. So now we're differentiating this, and let's see what happens when we take the, sorry, it's this times e to the lambda t, right? Of course. So x prime is equal to, well, I'm going to arrange it in terms of powers of t, because if you have as the things as equal as to a function of t, which are polynomials, then the coefficients of those polynomials have to equal. Because polynomials are extensionally determined by their coefficients, at least over the real numbers. So we're going to get t squared over 2, and then we're going to have to differentiate lambda in order to get a t squared. Then as for ways that we can get t, we can differentiate this. So we're going to get t, and then we're going to get, oh, sorry, this is times v1. Then the ways that you can get t are that you can differentiate this. So you'd get v1. Or you can differentiate e to the lambda t here, so plus lambda v2. And the ways that you can get something here are you can either differentiate, so I'd like to put the higher order term here. So we differentiate the t here, so we get v2 plus lambda v3. And now when we take ax, what that becomes is, well, this is relatively a constant. So we get t squared over 2 av1. So as for the first coefficients, it doesn't matter that we had a 2 here. We get av1 is equal to lambda v1, no matter what denominator we had here, right? However, what happens is for the second coefficient, if we wanted to be nice, then we had to have the 2 because we differentiated this and that's 2 came down and it canceled with that. So that's why we had the 2 there. So then we have t a v2. And then we have just a v3. And that all of this is by multiplied by e to the lambda t. So as polynomials of t, their coefficients have to equal. So that tells us that av1 is equal to lambda v1. Great. The next thing tells us that av2 is equal to, let's say, lambda v2 plus v1. In other words, we can rearrange these equations to give a minus lambda I v1 is equal to 0. A minus lambda I v2 is equal to v1. And here we get that a v3 is equal to lambda v3 plus v2. So that tells us that a minus lambda I v3 is equal to v2. So with this ansatz, with the 2 there, we get that the meaning of the vectors is that they're a chain, which of a minus lambda I sending v3 to v2, v2 to v1, and v1 to 0. And then if we can find any such 3 vectors, then we know what the solution is given our ansatz, right? But look, if we find 3 such vectors, then we also know a pair of vectors, and we also know an eigenvector. So once we do this procedure, we also know the previous 2 solutions that we get using the other ansatzes. So that's great. Now, what's the general case? So in general, if you have a sequence, if you can find so let's say vk, which gets sent to vk minus 1, which gets sent to eventually to v1, which gets sent to 0 by a minus lambda I. then what are these? What are the solutions going to be? So what are the ansatz is going to be that generate these things, right? We saw that as for this pattern, the ansatz that we took was this, right? So what's the general shape? Well, if you have a t cubed, what do you think the denominator is going to be?
3.
Well, how do power series work?
But you're only taking one derivative of it.
So let's try. So if we take the ansatz, let's say t cubed over 3 v1 plus t squared over, well, t squared, we should have a 2 here, right? Plus t v3 plus v4. Sorry, this is v1, v2, v3. Yeah, so t squared was the case where we had 3 and now we have 4. So if we differentiate, if we do the derivative, then what we're going to get is t cubed over 3. So lambda v1, that's good. But then for the next one, what's going to happen is that we're going to differentiate this. And so we're going to get t cubed, and the 3 is going to go away. But then we're going to get plus t cubed, so 1, or rather v1. And then here we're going to get the 2, and then the lambda is going to come out. So it's going to be lambda over 2 v2. Oh, no, that's not good, right? Because we want to have these two things equal, right? So what we want is to have a 2 here, which means that what should we have here?
A 6.
6, right? So in general, it's going to be like power series where we have factorials. So basically, that was, I'm going to erase this now because it only works when I sort of demoed it live. Now I'm just going to write what the answer is. Come on. Okay, that's how I erase it. Yes. So the ansatz is actually going to be that we have the solutions, well, x1. So the first solution that we can get is just from the eigenvector, right? So x1 is just going to be the solution v1 e to the lambda t, right? That's our eigenvector solution. Now, what's our next solution going to be? Well, that's going to be the second ansatz that we considered. And that second ansatz was t v1 plus v2, right? E to the lambda t. And then the general ansatz. Well, I'm going to write what the last one is, but it's sort of going to tell you what the general one is as well. It's going to be, so eventually, if we started off at the power 0 and we went k steps down, then the power would be t to the power of k minus 1. Because we started off at 0 and then we counted to k. So it would be k minus 1 divided by k minus 1 factorial. V1. Then I guess I can write the next term t k minus 2 over k minus 2 factorial. And then I can write the last two terms if they exist. V k minus 1 t plus vk. Right? Does that make sense? So I'm going to do an example. I mean, in reality, we're not going to go beyond 4 solutions. So the biggest ansatz that we're going to use is the, I guess, t cubed over 6 ansatz. That gives me 4 solutions. I think I'm going to do one example today of a 4-dimensional system. So for example, let's suppose that A is equal to the 4-dimensional system. So let's do an easy one. 2, 2, 1, 1, 2, 1, 2, 0, 0, 0, 0, 0, 0. Okay, so the first question is, how do I compute the determinants of A minus lambda I? Because how do I compute the determinants of a 4x4 matrix? And so the answer is that we're going to use, and I think that this is really only going to happen basically once, the cofactor expansion. And the idea behind a cofactor expansion is that if you have a general determinant, so I'll write this in a different color. If you have any matrix and you have values A1 through to A, let's say M, and then, okay, let's write it A11 through AM1, A1M. It should be a square matrix if we're going to be taking the determinants. AMM. And we want to take the determinants of this, so I write bars like this. Then what that's going to equal is we can express it in terms of determinants of smaller matrices. It's going to be, if I cofactor expand along a column, I could also cofactor expand along the row. I'm going to take this column and I'm going to choose to cofactor expand across it from it. So what I'm going to get is A11 times the determinants of what? Well, this entry sits up top a matrix right here, right? That's one size smaller. So it's going to be A11 times the determinants of A2 2 through AM. So that's the matrix that's right here. And then we're going to get plus A2, 1. And how it works is that this sits on top of a matrix, and that matrix looks like this, right? And so what we're going to do is it's sort of going to teleport. It's going to be A3, 1 up to A M, sorry, 3, 2 up to A M2, and then teleporting back to A1, 2. So do you see how that teleportation works? If you take this as sitting being above a matrix, then that matrix has this as its first column and this as its last column.
Usually they don't do the teleportation. Is that like for like to take care of negatives?
Oh yeah, so if you don't do the teleportation, if you just write it down naively, then you're going to get a power of 1 to the negative k. Because what happens is if you basically switching two columns changes the determinant by a sign. And if you sort of do the math, then not teleporting would add a sign that varies by -1 with each successive thing. But sort of, it's easier to just remember the teleporting version, I think. I like the teleporting version better. But you're right, that it's usually presented without teleporting. And then so on. And then a m1. And then here you'd have just, okay, let's see, there's a comment. Is there e to the lambda x for vector x? Oh, yes, the last vector should have, of course, I wrote e to lambda t everywhere else. Just to give me some room to actually write that. One of the dots got moved over. Thanks. And then if we don't teleport, then it just, for the last thing, it would just start here. And then it would end in a m-1. Sorry, a 1. And I should point out what the key fact is. The key fact is that this is a m-1 by m-1 matrix. Well, rather, it's the determinants of such a matrix. So the point is that you could use the cofactor expansion again to evaluate this. And so actually, the cofactor expansion gives you a way to solve determinants of any size. It gives you a recursive algorithm for computing arbitrary determinants. And in our case, if we do a cofactor expansion along this column, you could also do cofactor expansions along rows as well. Then it's just the matrix that sits where this sits to the top left of a matrix, and then it teleports across here. And you can do a cofactor expansion not just across the first one, you could do it across any one, and then it's just teleportation across both sides when you do that. So you can do it along any column or any row. And here is why the teleportation thing is objectively better. Because if you start doing it like along the kth column, then the negative ones have to, they don't start at just 1. They start off at 1 or -1, depending on the parity of k. And that's a bit hard to remember. So if you just remember teleportation, then you don't have to remember you can't be off by 1. It's just teleportation. Okay, so here the thing is that if we do cofactor expansion along this, that it's easy because only one of the determinants is going to be non-zero. So this is going to be, well, if we're going to do a minus lambda I, right? So basically what we get is minus lambdas here, but these entries are still 0. So it would be 2 minus lambda times the determinants of this, right? But with the minus lambdas. And then it would be plus 0 for the other things. So we won't even write out what the determinants are because the leading entry is 0. Now, let me just write that this is equal to start. And then let's put start here. And so what we had was that was some determinants. Whoops. There, I got everything and just a bit of the next equation. And for a 3x3 matrix, we can just do the determinant directly. So if we start here, we're going to get this, but if we do here, we're going to get 0 entries. And it turns out that in general, if you do the diagonals, it's always going to hit 0 for any one of these. except for this one. In general, if you have what's called an upper triangular matrix, the determinant is just going to be the product of the diagonal entries. So this is actually equal to, you can check that just using the formula, that only one of these diagonal products is going to be non-zero. So it's going to be 2 minus lambda to the power of 4. We have 1 here. So lambda, so 2 is an eigenvalue of multiplicity 4. Okay, now when we subtract the 2i from this matrix, we're going to get just ones on the super diagonal and zeros everywhere else. And so let's solve this. So we're going to get 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. And we want to find something in the kernel because that's going to give us an eigenvector. Well, what does that tell us? So if the eigenvector is A, B, C, D, if it's 4, you're going to use A, B, and C and D for the letters, right? So that tells us that B is equal to 0, 0. Like that. C is equal to 0, D is equal to 0, and 0 is equal to 0. That's what this equation says. So that tells us that, well, okay, we get to set A to be whatever we want, and we want something non-zero, so we're just going to set it to 1 for simplicity, right? So this is an eigenvector. And we're going to call this V1. Now, there are no more eigenvectors that are linearly independent from this, because these 3 have to be 0, so there's only 1 degree of freedom that we have. So undeterred by this, what we're going to do is we're going to find something that maps to this. And we're going to do this 3 times over. No way am I writing this again. So for the second round, the fig is that we change this 0 to be a 1 now. And so what that tells us is that B is equal to 1, C is equal to 0, D is equal to 0, and 0 is equal to 0. Well, now, what should we set A equal to?
Probably 0.
Yeah, because that we don't need it to be 1 in order to make the fig non-zero. And just changing it to be any number just adds a multiple of V1 to V2. So we don't care about that. So the simplest thing that we could write down is 0. And I'm not going to call this an eigenvector because it's not an eigenvector, but it's V2. Now what we're going to do is we're going to take this, and now we're going to consider the second entry as 1. So this tells us that B is equal to 0, C is equal to 1, D is equal to 0, and 0 is equal to 0. So we once again set A equal to 0. And we get V3 is 0, 0, 1, 0. And then finally, for the fourth round, we're going to put a 1 here. This tells us that B is equal to 0, C is equal to 0, D is equal to 1, 0 is equal to 0. We set A equals to 0. We get V4 is, so what we recover is basically the standard basis for the space. But that's because this example was chosen to be as simple as possible. So if A minus lambda I is just ones on the super diagonal, then in general, what you'll get is the standard basis. Okay, so what does that tell us? So we know V1, V2, V3, and V4. So what are our solutions going to be? what are the ansatces that are going to generate this sequence of things? Well, it's going, well, so some solutions are x1 is equal to v1 e to the 2t. x2 is equal to t v1 plus v2 e to the 2t. Then x3, so now we remember that since it's t squared, we have to divide by 2 factorial. And then x4 is going to be t squared t cubed over 6 v1 plus t squared over 2v2 plus tv3 plus v4 e to the 2t. Okay, so what we're going to do is we have 4 linearly independent solutions, and we're going to give this constant c, d, e, and f. And so basically how this is going to work is that let's think about the x entry, the y entry, the z entry, and the w entry. So v1 has 1 in the top position, and nothing else has a 1 in the top position. So as far as the top position is concerned, these are the things that contributes to the top position, right? Then these are the things that contributes to the second position, right? Then these are going to be the things that contribute to the third position. And then the fourth position is just going to be this. So if we combine all of the data together, what we're going to get is that x is equal to, so there's going to be an e to the 2t, but it's going to be c plus dt plus e t squared over 2 plus f t cubed over 6 e to the 2t. And now we don't care about x1 anymore because it doesn't contribute. Only these are going to contribute to the next position. So then we're going to get y is equal to, well, this is coefficient d. So d plus et plus f t squared over 2 e to the 2t. Then we don't care about that one anymore. Then we're going to get z is equal to e plus ft. And then we're going to get the w is equal to f e to the 2t. And that is your general 4-dimensional solution to the 4D system given by the matrix A is equal to this. So we've solved a 4x4 system of equations. I mean, if we write this down, what does this say? This says that x is equal to 2x plus, sorry, x prime is equal to 2x plus y prime is equal to 2y plus z prime is equal to 2z plus w, and w prime is equal to 2w. Well, technically, we could have solved this not using this method, but we could have back solved the last equation and then substituted it into the previous one and then substitute into the previous one because it's upper triangular. So we can solve the last one. It's independent of the previous ones, right? And then we can propagate the dependency up. So we could have also solved this directly. But now we're going to do an example where that wouldn't work. So now we're going to actually introduce not just an upper triangular matrix. General. And so it's not going to be a matrix. I'm still going to give you something easy because we don't want to just spend forever computing. Let's see, what time is it? 50. Yeah, this is going to be a long example. But yeah, sure, let's do it. So it's -1, 0, 1, 0. Another 4x4. 0, 1, -4, 2. 0, 1. So it's not upper triangular. There's a 1 here. -3, 1, and then just zeros here. So the cofactor expansion for the determinant is going to work great because there's only one of the cofactors is going to be non-zero. So the determinants of a minus lambda I is going to equal -1 minus lambda I. Sorry, -1 minus lambda times the determinant of this matrix. Sorry, there are minus lambdas here. Otherwise, we'd have a 0 row and then it would be 0, but it's not 0. And then this is +0. Okay, so let's just take this minus sign out, lambda +1. And then what we're going to do is we're going to do sort of the diagonal things with teleportation. And here we're going to get.
Could we like do it like the last row?
Oh yeah, that's a good point. So let's do a cofactor expansion. You mean at this stage, right? That's a better way to compute it. I think that's actually how the notes that I'm doing compute it. I decided to do it as a 3x3 matrix, but no, let's do a cofactor expansion. So the way that works is this is going to equal minus lambda, and then this is going to be supposed to sit to the top left of a thing. So with teleportation, it's this thing that it sits over. Good suggestion. And then the other things are just going to be 0. So what that's equal to is minus lambda +1. Then minus lambda. Multiplicatively. Then here it's going to be 1 minus lambda times -3 minus lambda, and then +5. So this minus and this minus cancel out. And anyway, we just want the roots, so we really don't care. And then this becomes lambda
Is it
squared.
+5?
Oh, 4. Thanks. Somehow I added them together, which is of course silly. Lambda, so this is +3 minus 1, so it's going to be +2 lambda. Then we're going to get a -3 here, +4, so +1. Oh, well, that's easy to factor, isn't it? So that's lambda +1. We have a lambda +1 here, so we get lambda +1 cubed lambda, right? Now, in general, we don't know that the kernel of this is going to be one-dimensional. There might be multiple eigenvalues associated to the eigenvalue 1, right? But sometimes we're going to have to do chains. As it turns out, it's going to be a chain of 3 in this example. But that doesn't have to happen. You might, with a 3-dimensional eigenspace, there are 2 possibilities. Sorry, with lambda multiplicity 3. You can get one of 3 things. You can get 3 eigenvectors, right? So you can get V1 gets sent to 0, V2 gets sent to 0, and V3 gets sent to 0. That's possible, right? The second possibility is that, let's say, V1 gets sent to 0, and also V2 gets sent to 0. but then v3 gets sent to v2. And what's the third possibility? So to give you the language, this is a chain of length 2 and a chain of length 1. And this is 3 chains of length 1. So here we'd get what?
The biggest chain.
1 chain of length 3. So yeah, exactly. v3 gets sent to v2, gets sent to v1, gets sent to 0. So with a 3-dimensional eigenspace, all 3 of these are possible. How would you know which situation it is? Well, you'd solve for the kernel, and then you'd see how many solutions you got, right? In the previous cases, it was clear that there was only like 1 degree of freedom, so we couldn't get a 3-dimensional kernel. And then you basically try, and if you found that there were 2 things, well, the third thing can belong to either of them, so you try and solve both of them. And in general, if you have things of this shape, they're guaranteed to be linearly independent. That's a math theorem. So if you find, I mean, assuming that the starting things of the chains are linearly independent. If the starting things of each of these chains are linearly independent, then the V3 is also going to be linearly independent for V1 and V2. Or in this case, these 3 are going to be linearly independent. Anyway, so let's do lambda equals 0. So lambda is equal to -1 or 0. However, it's already that's time. You know what? Let's do lambda equals 0 and then take a break. So for lambda is equal to 0, I again do not want to copy this down. So we're going to get this, except for the fact that we're going to erase this, and we're going to put a horizontal bar, and then we want something in the kernel. Well, what do you notice about the second and third rows? Sorry, we want to subtract No, never mind. We don't notice anything about the second to the third rows. So we're going to do row reduction. First off, let's just multiply this by 1 so that there's a 1 here. Now, let's take this and leave it as is. And what we're going to do is we're going to subtract this from this. So that's going to give us a 0. Then when we're subtracting 1, so we're adding 4 now, and that's going to give us a 1. And then we are subtracting 1, and here we're subtracting 2. So that's going to give us a -1. And then here, well, there were all zeros to start off with, so they're all going to be zeros to end off with. Okay, let's make more entries 0. So we have these ones in the diagonal, and that's great. Let's make more of these things be 0. So let's get 1, 0, 0. If we do this, then we're going to add 1 here and subtract 1 here, so -1. Let's make this 4 be 0. So we're going to add 4 here. And then that would mean if we're adding 4 here, then we're subtracting 4 here. Okay, just to finish the row reduction, at this point, do we really even need to continue? Let's just write out what equations this gives us. We don't need to row reduce it all the way to the end. So this tells us that A so let's say A, B, C, D. A minus D is equal to 0. This tells us that B minus 2D is equal to 0. This tells us that C minus D is equal to 0, right? And this tells us that 0 is equal to 0, right? So at this point, we have a degree of freedom. And it looks very tempting to just set D equal to something and then see what that gives us for the other things, right? So what happens if we set D equals to 0?
Not good.
Yeah, it's all 0. And so that's not a non-zero eigenvector. We want a non-zero eigenvector. So let's do the next simplest thing and set D equals 1. And notice this is basically one degree of freedom, because once we set D to be something, every single other thing is determined, right? That means we're going to get a one-dimensional eigenspace. So there aren't two linearly independent eigenvectors. There's only one eigenvector. Well, one dimension of eigenvectors. So if D equals 1, then, well, A equals D. So 1, 2, 1. And then we set D equal 1, so 1. So this is an eigenvector. Well, I mean, it was a way, this eigenvector had multiplicity 1 anyway, so we wouldn't expect more. We're doing the multiplicity 1 eigenvector. So this is an eigenvector for lambda equals 1. And now we have to do the case of lambda, sorry, for lambda equals 0. And now we're doing lambda is equal to -1. Except we're going to take a break and we're going to resume out. Let's just take an 8-minute break and let's resume at 8:10. Okay. resuming, and I'm not going to hold my blow high for the last hour. Let's just do this. So now we want to solve for, we're going to take minus lambda I, so plus I to this matrix, and the diagonal entries are going to change as a result. So we're going to do +1 to the diagonal entries. So this becomes a 0. This becomes a 2. This becomes a -2. Wait a second. Wait a second. That's bad. What? No, that's good. That's good. That's actually good. No, this is really good. Right, so we get a 1 here. What's that 1 is going to tell us is that d is equal to 0. So this isn't a contradiction. It would be a contradiction if we had zeros here and then a 1 here, right? That would be a contradiction. But if we have a 1 here and a 0 here, that just tells us that d is 0. Okay, now what do you notice about the second and third rows of this matrix?
They're equal beside for the C position.
I mean, one's twice the other, right? There's a multiplied by 2 for rows, right? Here. So basically we can eliminate, let's eliminate this one. And also, what should we do? You know what? At this point already, we can write out the system. Let's write out what this gives us. This gives us that C is equal to 0. 0 is equal to 0. That B minus 2C plus D is equal to 0, and that D is equal to 0. Well, D is equal to 0 means that D is equal to 0. And then C is equal to 0 means that C is equal to 0, right? So B is also equal to 0. And so our only choice is A, right? And so setting A to 0 would be bad, so we set it to 1. One, 0, 0, 0 is an eigenvector. And this we're going to call V1. And there are no more. It's a one-dimensional eigenspace, right? So if we have a one-dimensional eigenspace, I showed you what the 3 cases are, then it has to be the third case, right? It can't be the second case because we'd have 2 linearly independent eigenvectors in that case. So we're going to play this game a few more times. So now what we're doing is we're changing this 0 to be a 1. Now the same row reduction happens. We still have that this is a multiple of this. So this row becomes 0 except for the fact that I have a 1 here now. And so what that tells me is that C is equal to 1, 0 is equal to 0, B minus 2C plus D is equal to 0, and that D is equal to 0. So what does that tell us? So D is equal to 0, C is equal to 1, which means that B is equal to 2. So B is equal to 2. C is equal to 1, and D is equal to 0. Now, what are we going to let A be?
Zero.
Yeah, because it's a simpler thing and we don't need it to get a non-zero eigenvector. And notice that if we make A be non-zero, that it's just going to add a multiple of this. So we don't care about that because that gets sent to zero. So no matter what, we're going to get a V2 that works. So V2 is going to be 0, 2, 1, 0. Now, this is, we expect three-dimensional generalized eigenspace. So this is going to be our last time playing this game. Oh, look at this. We put the numbers 2 and 1 here, and these still remain multiples of one another. How fortuitous, right? Well, I already have that arrow here. I guess I can erase both of those and clean this up. And so that went away, but this is still a 1. So that tells us that, except that entry is a 0, the top entry is a 0. Right, we should be careful when copying things to actually make everything reflect the way that things are in this state. So this tells us that C is equal to 0. That's 2B, well, then 0 equals 0. Then B minus 2C plus D is equal to 1 now, and that D is equal to 1. Sorry, D equals to 0. So D and C are equal to 0, which tells us that B is equal to 1. Again, we can set A equals 0. And so then we get that V3 is 0, 1, 0, 0. So V1 and V3 are sort of nice, but it turned out that V2 sort of had a surprising form, so that no one expects. But okay. I will do, since I have not 2, 4, let's do 20. Okay, so in summary, we have V1, V2, and V3. And just to write them down, what they look like is 0, 1, 0, 0 gets sent to by A minus I, sorry, A plus I. I should write that in blue, that's how I've been doing it. And then the second one is 0, 2, 1, 0. And the first one was just 1, 0, 0, 0. And that gets sent to 0. And then I guess separately, we can consider the case lambda is equal to 0, just to write out all of the data in one place. For lambda is equal to 0, we had 1, 2, 1, 1. And that gets sent by A minus 0i, so just by A. to 0. So in summary, basically, if we have an n by n system, then we're going to get n vectors be living in generalized eigenspaces. And so we're working in a 4x4 system, and so we are going to get 4 vectors. Not all of them are going to be eigenvectors. Some of them are going to be generalized eigenvectors, and we get a picture like this. And so from this, we can sort of write down what the solutions are. So from this, let's say we get a solution x1. Now this is to the power of lambda 0, right? So e to the lambda t is just going to be 1. So x1 is the solution 1, 2, 1, 1, right? Just constants, multiples of this. x2 is going to be the eigenvector solution. I actually want to not scroll down and have these on the screen at the same time. x2 is going to be the eigenvector solution corresponding to this. So it's going to be 1, 0, 0, 0. The eigenvector, the eigenvalue is -1, so it's going to be e to the minus t. Then we're going to get x3, and this is going to be the ansatz that we discussed when we started this, which is going to be t e to the minus t times x1 plus e to the minus t x2. If I want to fit all of this in one line, this has to move all the way to the end. And x4, which is probably not going to fit, is going to be t squared over 2 e to the, let's keep the e to the minus, okay, the e to the minus t's are going to waste a bunch of space. 1, 0, 0, 0 plus t e to the minus t 0, 2, 1, 0. I knew it wasn't going to fit. And then we can give this one a bit more space. Although this one now looks scrunched up. Plus v3, 0, 1, 0, 0, e to the minus t. It was in the second position, right? Okay, so let's associate this with the constants c, d, e, and f. And let's see, basically every single one of these contributes to the first entry, right? So we're going to get that x is equal to, then let's see. So c and then we're going to get plus e to the minus t. Then we're going to get d. Then we're going to get e times t. And then we're going to get f times t squared over 2. Right? Now let's look at the second entry. So the things contributing to the second entry are C, E, and F. D doesn't contribute. So here we have a 2, so it's 2C. Then D doesn't contribute. E contributes as 2. and then F contributes as T. F to T. Oh, and then I see. It contributes also from this one. So it's going to be F times 2T plus 1. Cool. Z. What do we get? We get a 1C. Then this doesn't contribute, this contributes. And then this contributes. So it's going to be plus e to the minus t. Okay, let's see. D doesn't contribute, E contributes 1. And F contributes T. And then we have W. And as for W, these are all zeros. And then here we have just a C. So this is the general solution. And with this, I mean, this example had some zeros, and the cofactor expansions were sort of not the hardest that they could possibly be. But this is basically a pretty general example that covers all of the bases. So at this point, since you know the cofactor expansion, you can solve arbitrary constant coefficient homogeneous linear systems of arbitrary dimension, right? At this stage. Because I've already told you what the ansatz is for these generalized eigenspaces. So this example was this one. And cool, we're able to solve nice 4x4 systems. I mean, this had all zeros here. Well, that's why we had that lambda equals 0 eigenvalue. But yeah, sure, they could have also been numbers. We didn't lose that much generality. This is pretty general. How much time do I have left? I have half an hour left. Okay, so now I made a bad mistake. I'm going to talk about something, and that something is actually not the next thing that I should talk about. So the next thing that I should talk about is how to solve inhomogeneous linear systems. However, I forgot about that, and so I moved on to the next topic. So we are going to talk for 30 minutes about a topic, and then at the start of next lecture, we're going to do inhomogeneous linear systems. So sorry about that. So inhomogeneous linear systems next time. Before we move on, does anyone have any questions about this example or the general methods that we've outlined? Okay, sounds good. So I think that like in a theoretical linear algebra class, at the very end of a full semester's course, you get to doing calculations like this, because it's not about doing calculations like this, it's about doing the theory. So if you want to understand all of the theory underlying this, you have to spend a semester talking. But if you would just want to do row reduction goes burr and calculate things like this, then we could do it in 2 3-hour lectures. That's not an issue. So you don't know theoretical linear algebra just from the stuff that I've exposed you to in this class, but you do know how to do row reduction, and that's good enough for solving differential equations, systems of differential equations. So we've also covered what happens when you have complex roots. Now, I guess you can ask what happens if there's a complex root of higher multiplicity. Well, you could also get this situation where you have where you have a generalized eigenspace. But I'm not actually going to do this in practice. So technically, you could combine both of these together and have a generalized complex eigenspace. That's also possible. But I mean, it's not new. You already know how to do that. Okay, so let's just completely switch topics and talk about operators. And this is going to be working up towards Laplace transforms. So an operator, which we'll refer to as, let's say, L for now, is something that takes functions to functions. There's a question in the chats. Yeah, so in Math 310, that's the theoretical linear algebra class. And then, for example, the justification for why you have these generalized eigenspaces and why they look like what I did is Jordan form. So if you talk about Jordan form, that justifies the method that we're currently doing. That would be the theory behind it. But discussing, okay, operators are also discussed in linear algebra. What is an operator? An operator is just a linear transformation from a vector space to itself. But in this case, we're going to think about the vector space of functions. We're going to think about functions. And so it's something that takes functions to functions and is linear. So we're going to consider operators on function spaces. But I'm not going to say on function spaces. That is, and the way that I'm going to write an operator applied to a function is I've just chosen completely randomly to use angle brackets. Not angle brackets, these are square braces. So if you have f plus lambda g, where lambda is a number, then this should equal L of f plus lambda L of g. So I'll give you an example of a great differential operator. Let's consider L is equal to what we're going to denote as D, capital D, which is the operator differentiation with respect to, I'm now going to return to using X as the dependent variable and Y is the independent variable, not T. So Y is going to be a function of X now, ddx. Well, differentiation is linear, right? If you scale a function, then the derivative also gets scaled. And if you take the derivative of a sum, you get the sum of the derivatives. So differentiation is linear. Great. Now, what I'm going to do is if P of X is some polynomial, then I'm going to evaluate the polynomial on a differential operator. So P of D is going to equal a to the n d to the n plus dot 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 plus a naught is a differential operator. Well, it's just an operator. Is an operator. And we'll call this. So I call it a polynomial operator. Maybe I'll put differential brackets. So we're basically going back to the theory of constant coefficient linear equations. Because in constant coefficient linear equations, so for example, if we have the equation let's say y prime prime plus 2y prime plus y is equal to f. So the inhomogeneous equation is P of D applied to y is equal to f of x for P of x is equal to x squared plus 2x plus 1, right? So basically, if we take this polynomial and we replace the x's with differentiation, we get the operator which we can apply to y to get this expression right here. Now, a theorem which I'm not going to prove is that if P and Q are polynomials, then if we take P times D and we apply, P and Q, P times Q, and we apply that to D, that's the same differential operator as P of D composed with Q of D. And usually we won't write composition. Usually if I just write two differential operators beside each other, I'll mean composition. So this is the operator that does Q of D first and then P of D to the results. So we're going to accept this without proof. But what does this mean, for example? Well, if we have x squared plus 2x plus 1, then that's equal to x plus 1 times x plus 1. So d squared plus 2d plus 1 is also equal to d plus 1 times d plus 1 in the sense of composite with things. So basically what I'm saying here is before we justified sort of factoring these expressions, and factoring these expressions is justified in general because if you have a product of polynomials and you evaluated a differential operator, it's the same as composing the evaluation on both polynomials. And multiplication of polynomials is commutative. Therefore, these operators also commute with each other. Where by commutes, I mean that, so as a corollary, since multiplication of polynomials is commutative, P of D, Q of D, well, that's equal to P times Q of D, which is the same as Q times P of D because they're just, the multiplication is commutative. So that's Q of D times P of D. So if we have something with distinct roots, let's say what happens if we take something like x plus 1 times x plus 2. Well, that's equal to x squared plus 3x plus 2, right? Well, actually, why am I even doing this? Why am I expanding this? I don't need to expand it. We don't care about this. So for this, we have that P plus 1, D plus 1. Times D plus 2 is equal to D plus 2 times D plus 1. So we can rearrange factors as well. So I'll give a computational example. Compute d squared minus 2d minus 3 of sine x plus x squared. And I'm going to do this in two ways. So this factors, but first, oh, you have your hand up? Go ahead.
Could you replace d by like any operator? Does the theorem still work?
Yes. Yes, it does. The reason that the theorem works is that any operator commutes with the identity. And so it's because every single expression here in sight, because there's implicitly an identity operator here, because they all commute, you're allowed to do rearrangements. If you, however, had D and F, where D and F were two different operators that did not necessarily commute, then this would not be allowed. But you're right. This works equally well, works with D replaced by L. So long as there's no other operator. And let's write the other operator as sort of like, how do I write a script F? This is how I write a script F. So long as there is no other F, basically. If it's just L and the identity, then this works. Good observation. Okay, so let's do method one. This is sort of going to be checking that the theorem holds by doing it in two different ways. So method one is we're going to consider, it's linear, so we're going to split it up as d squared minus 2d minus 3 applied to sine x, and as d squared minus 2d minus 3 applied to x squared. And at this point, we're just going to be able to evaluate this. So like if we take the derivative of sine, we get cosine and then minus sine. Minus 2 cosine. Minus 3 sine. Then what do we get here? Well, we differentiate x squared twice, we get 2 minus 4 x minus 3x squared, which we could also rewrite as minus 3x squared minus 4x plus 2. Then I put my cosine first, minus 2 cos x minus 4 sine x. Cool. Method two. By the way, I should post assignment 2 soon. Like I should do it within the next 24 hours, realistically speaking. And probably assignment 2 is going to cover up to the end of linear systems, because I sort of extended assignment 1 and we went long enough that linear systems are already covered. So this is going to be the scope of coverage of assignment 2. So it's going to also have like second order differential equations, and we did a bunch of stuff there. So it's going to have a bunch of material on it. Ow, my fingers hurt so much from writing. I didn't used to have a writing callus because I mostly sort of program instead of just writing math. But it's been developing again with giving 9 hours of lectures and writing with, you have a Wacom tablets. It is really good. It's like $120 or something. And it basically lets you do math on a computer, not in the proof assistant sense, but in the collaborating with others and sharing whiteboard sense, the social sense of doing math on a computer. Okay, so methods 2 is we have this original expression. And what we can do is we can factor this and notice that it's d, it's going to be -3 and d plus 1. In my notes, I did it in that order. We could have also done it in the other order. So this is going to equal to d minus 3 applied to, now we're just going to differentiate this. We're going to get cosine of x plus 2x. And then we're not going to differentiate that. And we're going to get sine of x plus x squared. And then we're going to differentiate all of that. So we're going to get minus sine of x plus 2 plus cosine of x plus 2x. And then we're going to not differentiate all of this and subtract 3 times that. I think, yeah, I really don't want to write anymore today. And so what that gives you is, well, let's rearrange. So minus 3x squared. That's going to be your x squared term. For your x term, you're going to get 2 minus 6, so it's minus 4x. Then for your constant term, it's just going to be 2. That's the only one. And then for your cosine, you're going to get 1 minus 3, so it's going to be minus 2 cosine x. And then we're going to get just here is a sine, and here is a minus 3 sine, so minus 4 sine x. And we can check that this matches up with our previous answer. And so because it matches up with the previous answer, you can also probably believe that it would work if we matched it up with interchanging these two. So like the math explanation for why this theorem holds is because the things in the question commute with each other. And that's sort of the best math explanation that I can give, but you need some sort of intuition to be able to grasp that. But here we tried it in practice and we saw that it worked. Do I have time to talk about the next topic? I do have time to talk about the next topic. So now we're going to do an exciting theorem about this. Just do 1,000 more, and I think we're going to, that's going to be enough. And this theorem is called the exponential shift theorem. And I have ventured far enough that I think I'm actually going to do the proof of the theorem. I'm going to prove a theorem. This might be the very first theorem that we're actually proving in the course. And what the exponential theorem says is that if you have a polynomial operator, so P of D, polynomial differential operator, and you are applying it to some function u times e to the ax, then what this is equal to is we're going to consider the differential operator e to the ax times p. So this is the operator that just multiplies by e to the ax times the differential operator p of d plus a. So we're going to plug in d plus a instead of d into the polynomial. And then this is going to be applied to u. So you know what? I think that instead of proving the theorem, I'm going to show you how to use it. That's sort of a better use of time. So proof next time. And let's do an example. So let's say we consider the differential operator d squared plus 2d plus 3. And we're going to apply this to e to the 2x sine x. Now you could manually compute this, and it would actually be very painful and very boring, is how it would go. Let's use the exponential shift theorem. What that says is that this e to the 2x can come out front. But what's going to happen when it comes out front is that d is going to be replaced with d plus 2. Applied to sine of x. And so what that's equal to is e to the 2x times d squared. Then let's see what the term is. It's going to be 4d here and then 2d, so plus 6d. Then what do we get here? We have a 4. We have another 4, so that's 8. Plus 3, so that gives us 11. So what that's equal to, and now we just do it. If you differentiate sine twice, you get so minus cosine. Plus
minus sine.
Sorry, minus sine. Thank you. Here we get plus 6 cosine. Plus 11 sine. And okay, so we can rearrange this to e to the 2x. And then we'd get 6 cosine x. Plus 10 sine x. And if you want to actually do it at home, you can try to do this manually without using the exponential shift theorem. So you can differentiate this and then use chain rule. So here you'd have to use chain rule twice. So you see when I say using chain rule twice on this term, it's going to first expand it to 2 terms, and it's going to expand it to 4 terms. So this is going to give you 4 terms, this is going to give you 2 terms, and then you're going to have this. Then you're going to have to combine them all together. And that's boring. And this is a quicker calculation, and it's much more interesting in more difficult examples. So instead of proving the theorem, I guess I'm going to end 5 minutes early. So are there any questions? Homework is due at midnight tonight on Blackboard. Has anyone had trouble accessing Blackboard or stuff like that?
I still don't have access to it. So can I just email
Wait, are you sure that you don't have access to
Yeah, I
Blackboard?
haven't gotten an email or anything. So I have no
Do
idea.
you have a Stony Brook email address?
I wasn't emailed anything about it, so I don't know.
You do have a Stony Brook email address. At this point, it's provably true.
Okay.
Okay, you can email me the assignments for the time being, but I'm going to want to grade it on Blackboard. So can you please email? So the person who does this retired. That's the problem.
Yeah, so nobody's giving me any information. I don't actually go to this school, so like I
guess that. So I send me the assignments tonight, and I'll send you an email saying who you should email.
Okay, perfect. Thank you.
And then you're going to email them, and then they're going to give you access to Blackboard, and then you're going to upload it to Blackboard. Because I need to grade it there, because I grade it on like the software, and if I just have a PDF, this application doesn't just let me write on PDFs. It's sort of a deficiency on OS X. There are like there's lack of applications that let you write on PDFs. Anyway, okay, so that's going to happen. Cool. Anyone else? Okay, that sounds sounds like a plan. So I expect all of your homeworks to be in tonight. And then the first thing that I'm going to focus on is writing the next assignments. Then I'm going to focus on writing solutions for this. And only after that am I going to grade stuff, and do not expect punctual grading. That's just not realistic at this point. There's a question in chat. When is the assignment going to be due? A week after I post it, which should be within the next 24 hours. Okay, see you tomorrow. Bye.